All right. Hello, everyone. Welcome back to Theory Track. We don't have the greatest attendance today because, it is midterms, but this is why we record things, right? So this week, we're going to be talking about embeddings, LSTMs, transformers, and LLMs. We're going to kind of go through the agenda for today and kind of just go through exactly what we will be talking about. So last time we talked about CNNs and modern CNN architectures, and we talked about RNNs. So, you got a glimpse at what deep learning is and kind of like why we use the things we do today and why deep learning started in 2012. And we also very briefly talk about RNN so you know how to kind of process sequential data. And today we're going to be kind of moving towards natural language processing and how that field has been dealing with their own data, throughout the years, because the field, as with natural language, is very, very sequential. Here's the attendance code. Here's the asset cluster if you want to follow along the slides. So without further ado, let's get started. This is a kind of roadmap that we have been following for Theory Track, and we're currently here in week 6. Next week is going to be President's Day, so we're not going to have a workshop. But on week 8, we're going to have another Venkat proof space thing special, where we're going to talk about ensembles and epsilon TP privacy. And week 9, we're going to talk about deep generative models and modern deep learning. Again, let us know if there's anything you want us to cover, and we will very happily add it. Okay. So this is old things. Okay, so let's start with what word embeddings are. Now, the thing is, we have talked about what neural networks are, right? Neural networks usually take in vectors as their input because, we're dealing with mathematical objects and we're trying to, work with this data. The question becomes, how can we represent words as vectors? How can we input words into our neural networks? Right. And in natural language processing, when we're dealing with sequential data, example problems can be something like the baseball player ran over to catch something, right? What do you think that blank can include? Any ideas? The ball, exactly, right? It can be literally anyone else. Maybe there's a criminal on the field and the baseball player went to catch them, The grizzly bear goes to the river to catch the fish, right? So like these sort of complete, fill in the blanks questions depend on the context of the sentence, right? So and we can use clues such as that, oh, bears typically go to the river to catch fish and things like that. These are kind of inherent knowledge that we have in our brain that we can use in these fun, complete the blank problems. So our goal is then to say, can we then necessarily let a machine learning model learn these things? So the naive approach is, what if we just count the number of occurrences of each word and just, we have a distribution of here are the words that exist, here are the number of frequency, like these words exist, and we just go from there. But the problem is this. This approach is actually called bag of words. It's actually one of the earliest ways that people have been trying to encode natural language into a sort of mathematical representation. Houston, we have a problem, which is we can have something like, wow, this presentation is bad, not good, and wow, this presentation is good, not bad. If you were to tally up the number of occurrences of each word in these two sentences, they mean very different things, in fact, completely opposite things. But if you were to tally them up, their kind of distribution of word occurrences will look exactly the same. So that's why we need context, right? So the ordering of the words matter just as much as what words are there in the sentence. Here's another example. Let's eat grandma versus let's eat grandma. Not only is like the order of the words important, but the way that we're saying these words, punctuation, and also the context also matters a lot. If you are talking about some sort of horror-based fairy tale, then the second sentence makes a lot of sense. But in the first example, maybe situations where we're talking about family dinners make a lot more sense, depending on how you define family dinners, right? So so to solve these problems, try to address these, we introduce something called embeddings. And inherently it is this. What we want to do is try to represent words as vectors, that somehow these vectors should capture the meaning of our input words. For example, as you can see here, father could point to girl and son, and like certain semantic information that we have about words should also correspond to the sort of mathematical representation that they are as vectors. The classic example that a lot of people use is something like king minus man plus woman should closely represent something like, any ideas with this? Queen, exactly, right? Awesome. And like if we say just do king minus man, maybe it will most closely represent say emperor or something like that, right? Something, more gender neutral. But the idea is that we want to somehow have a collection of vectors, one corresponding to each word that we define as here are all the words in the English dictionary that a user would reasonably input. We want to have a vector corresponding to every single one of them, usually a much lower dimensional vector, like 128 dimensions or 256 dimensions, something like that, that can correspond to the meaning like this, that is able to encode something about their meaning in this way. So the question becomes, how do we get these vectors? Your intuition is like, correct. This example illustrates how word embeddings are essential to generating information-rich encodings. That's the term we use, information-rich encodings, because what you can do is something called a one-hot encoding, which is, let's say we have 10,000 words in our dictionary, right? Then if, say, the very first word is the word queen, right? Then we can represent that word with a 1 in the very first dimension and 0 in all the other dimensions, right? And then the second word will be, say, king. And then there'll be 0 in the first dimension, 1 in the second dimension, and 0s in all the other dimensions. We call that one-hot encoding. That is something we can use, but you can quickly see how that's very inefficient, because the moment we add one additional word, the number of dimension gets bigger, and most importantly, the number of dimensions is huge, and it doesn't actually capture, the sort of relationships between words. So the earliest example of this is something called word2vec, which is, as the name suggests, turns words into vectors, and it is one of the I believe it is from Stanford, and it's one of the earliest examples where they try to use neural networks to try to capture to try to have this correspondence between word and embedding. And there's many other techniques such as CBAO, which stands for continuous back of words versus skipgram, and they both do a very similar thing, which we will talk a little bit about later when we talk about embeddings. But the idea is that, as I was talking about, with one-hot vectors, this sort of one-hot vector essentially indexes your entire dictionary. And when you have a list of, kind of your embedding weight matrix, when you have this one-hot vector as your inputs, you can do a multiplication, and it basically selects the row that you want, which is very convenient for us. It's just like a nice mathematical representation. So, is that question?
How is the embedding weight matrix like chosen?
So basically, usually it is trained. We will train some sort of model that will take the embedding matrix to do some downstream task. And in able to do that downstream task, we necessarily have to learn an embedding weight matrix that captures these information. I'll talk a bit more about this later. But like this is what we want, right? Like the key thing about word embeddings and just embeddings in general is that you have this sort of correspondence between here is a discrete thing, like a word that we have defined as a word, and a sort of like list of matrices to all the possible discrete things that you have to it, if that makes any sense. So that's what we want to arrive at. And the goal is to say, how can we learn this embedding weight matrix? Can we figure out what these rows in the matrix should be, which corresponds to each word? And to do so, we have to do something called tokenization. It is kind of like cutting a sentence into bite-sized pieces, because basically what word embeddings are is they're saying words are the smallest units of language, which for those of you who are in linguistics knows that's not true, but this is a good enough approximation for us now, right? If we were to say count a sentence as our smallest unit, there are a lot more sentences out there than there are words, and that's not very practical. So we usually start with words. So that's what tokenization aims to do, is saying if we have, say, I love pizza, we want to somehow cut it into, its individual parts, like I, love, pizza in a list. And there are many different ways of tokenization. There is the word tokenization that we mentioned. There is character tokenization, which is you can actually tokenize it to each character. That may make things really nice because we only have really 26 characters, maybe uppercase, lowercase, we want to make that distinction. Like a number of Unicode characters is not that much. So like this makes for a much smaller dictionary that we need to worry about. But you can see how like learning relationships becomes a lot more difficult because we're dealing with much more fragmented things. There's subword tokenization, which is kind of what ChatGPT does. Again, our team will talk a little bit about how ChatGPT does this. It does something called bytecode encoding, which uses some like compression scheme to figure out the best pairs, clusters of characters that are able to create tokenization, and there's obviously sentence tokenization, which usually nowadays with sentence tokenization is based on large language models that will take word tokenization, does some stuff to it, and then generate a sentence embedding. But the idea is that there's different ways of doing tokenization, and we're going to stick with word tokenization because it's very intuitive to us. And so yeah, like there's bi-pair encoding, which is something that ChatGPT uses, something like this, right? So yeah, there are many different ways of tokenizing words, and just like how there's many different ways of cutting pizza, some better than others. And one of the questions is, how do we cut something like this? ARNs, right? And these are all sort of wrong ways to do it. Like like there's things that you shouldn't do, like divide up a word completely randomly. And there's some things that people have figured out can be done, such as just doing on a whole word level. There's also something called lemmatization, which is basically saying if we have like I went there versus I go there. Went and go in this case are just different tenses of the same word, and sometimes we just lemmatization basically says let's take these like tenses and just change them all to present tense, get rid of plurals and stuff like that, so like we have less words that we're dealing with. So there are trade-offs between the different types of tokenization. Right. So now we have learned how to tokenize words. We can then convert these tokenizations into actual embeddings. So to answer the question of how are these embeddings actually learned, and the answer is basically by feeding these embeddings into a model that does some downstream task. So for example, I'm not terribly sure if this is exactly what Word2Vec did, but one of the classic ways to actually train these embeddings is, for example, you create a different neural network that is also just randomly initialized, and it takes in, say you have a sentence, it takes in a sequence of text, right? It takes in a sequence of text that has been converted to an embedding, and those embeddings will be randomly initialized. So if you have this weight matrix over here, originally it will be randomly initialized. Then what you say is, okay, we have this randomly initialized weight matrix. Let's feed the sentence, which just becomes a list of vectors, into that model. And the model, say, does the task, which is given a sentence of 8 words, I give the model the first 7 words. What is the 8th one, for example? Or we can do something more bidirectional, like here's a sentence of 8 words. I give the model the first 3 and then the last 4. What is the one that's missing? Some sort of prediction task. That's the classic way to do it. There's a lot of, you can see how, as long as we define some sort of task at the end where the model has to necessarily learn the meanings of words to be able to complete that task, as that model learns how to classify these things, because we're backpropagating the gradients all the way back to this embedding weight matrix, this embedding weight matrix must necessarily start learning the representations of these words. And you can also kind of see how if, say, in our kind of corpus of dictionary, if, say, a word never occurs in our data set, then what happens is the gradients will never pass on to it. So we also want to make sure that, hey, the dictionary has, in our core corpus of data, we've actually seen this word before. There's a lot of minute details to that, but the idea is we're using this embedding weight matrix, which is randomly initialized, passing it into some model to do some downstream task that requires us to understand this language, or honestly anything else. And then as we pass gradients and as the model becomes better at doing this prediction task or whatever downstream task we're doing, we necessarily have to learn an embedding weight that also captures the meanings of those words, because then the model's able to use these meanings to make predictions. Does that make sense? Okay, yeah. Again, that's a very big generalization. Like I believe Word2Vec and some other earlier models, they did some like cosine similarity thing depending on positions of words and sentences and stuff like that. That's how they made predictions, which is just, hey, if like given these words prior, let's just figure out like the one that has the closest cosine similarity to like some collection of it before with some other stuff. But the idea stays the same, which is like we have some downstream tasks that we have to learn. So that's how word embeddings work on a very high level. Does that kind of make sense? Any questions? Okay, cool. So now let's talk, now that we know like sometimes when how embeddings work, let's go into some architectures, like specific neural network architectures, where we may want to then pass these embeddings into to do some downstream tasks to see how you may practically actually define a model that will help you learn these embeddings. And one of these things is something called a recurrent neural network, which we talked about last time for processing sequential data.
So now we'll be talking about recurrent neural networks. So just to give you guys a brief overview of what we were discussing last time, recurrent neural networks are neural networks used for sequential data. That means that, suppose, for example, you have stock data where the sequence is in terms of time. You have this time step, you have the next time step, and so on. Or like semantic data with text, right, where you have one word after the other. That's what we would call sequential data, because the sequence, the order of the inputs matter. And recurrent neural networks are one way we can capture the order of the inputs. The way recurrent neural networks work is that they take an input, right? They output, at least initially, they take an input, they output an output, and then one of the hidden layer values is used as the input of the next time step. So in this case, for example, you have an input X, right? And then you have an output, but the previous hidden value is inputted again into the next time step, right? And all you do is you take the previous hidden value and you multiply it by weight matrix, then you add it back into the next time step. So think about sort of your neural network unfolded over time. So it's the same neural network. Is this all you're doing is that you have this recurrent relation where you input something, you take a value that it outputted from somewhere in the middle, somewhere in the hidden layer, then you input that back into the network for the next input, right? So for example, the first word might be the, right? Like the brown fox jumped over the fence, the quick brown fox jumped over the fence. You guys know that saying? The first word might be the neural network takes it, outputs some word embedding, for example, right? And we take the hidden value, the hidden value of this network, and we input that back into the network in the next time step. So in this case, quick, we would also consider the word the, right? And so that's basically the essence of recurrent neural networks. They have these recurrence relations where they take into account the previous sequential data. One big problem with recurrent neural networks is that they're really, really bad with long-term dependencies, right? So if you have, for example, a really, really long piece of text, it's really hard for the recurrent neural network to take into account the word in the beginning, or the semantic meaning in the beginning of your passage, because due to reasons because of this recurrence relation, right? Each time the recurrent neural networks unfolds, it becomes harder and harder and harder to train the previous parts of the network. And one of the reasons is partly because of the vanishing gradients problem. As we were talking last time, if you guys were here, we talked about how the way we train these models is it's a technique called backpropagation through time, right? So we take the same model and we unfold it over the time steps. And we consider every single time step to be sort of a layer in our neural network. So we unroll our neural network over time. And this, especially for long-term dependencies, when you have thousands of words or sometimes thousands of pages of text, it becomes very hard to train those early time steps, because over time, those gradients multiply and they get smaller and smaller and smaller and smaller and smaller. So the vanishing gradient problem is a big problem for recurrent neural networks. That's why we rarely use this in this form, right? This is sort of the vanilla form of recurrent neural networks. We really don't use it in this form, and we'll see what we actually use and how we can solve this problem. So we're going to be talking about long-term, short-term memory. It's a pretty cool topic. Let's get into it. So long-term, short-term memory, right? Long-term, short-term memory is it's kind of like RNN, but with steroids a little bit. It's like a much powerful version of RNN. It still has that recurrent neural network structure, but now it has a sort of a memory that's kept, sort of like a memory state that's kept. That's very different from the memory that we saw in previously, right? So pros. The first pro is that it solves the vanishing gradient problem. Not fully, but it does solve it at a much better rate than the vanilla RNN. And additionally, it's a little bit better with long-term memory, but still there's an issue with long-term memory. That's why transformers and so on work better. And cons is it cannot be parallelized. This is also a problem with RNNs, as they have sort of this recurrent structure, and you can't put in all of the sequential data to the GPU at once. you need to wait for every single sequential data, every single sequence, every single time step to be processed before you get to the next one, right? And so they cannot be parallelized. And in a world where GPU parallelization is basically, it's the key to like a lot of aspects of machine learning today, this is a very, very important point that must be stated. And to get into, before we start, does anyone have any questions on RNNs and just like the start of LSTMs? Nope, that's good. All right. So let's start with the LSTM module. So just to give you guys sort of like a preview before we get deep into it, this is the same module, right? It's the same neural network. It's just we're unfolding it over time. So this is the previous time step. This is the current time step, right? And this is the next time step. So this is the same thing. The reason we do this is to make it easier for you guys to understand how the model works, right? So we're unfolding the neural network over time. That's all that's happening. And these are all of the labels. Anytime we have, for example, in this case, anytime we have two lines coming together, we're concatenating the vectors. And anytime we, that's just vector transfer. Anytime we sort of like diverge, we're just copying the vectors into two, or copying the tensors into two. So let's get into some of the key parts of LSTMs. It's current input. This is just the current input to your text, or sorry, to your sequential data, right? For example, the quick brown box jumped over the fence. The might be your initial input. A quick might be your next let's say, quick, this is your current input. The previous input was the, right? It just goes like that. That's basically what your input is, the current input at the current time step, and the hidden state, right? The hidden state was the previous output that you had, right? And so in this case, the previous time step, you had an output of your module. And keep in mind, this is the same module, it's just over time, right? I just want to keep that quite clear. It's the previous output of the module. That's what your hidden state is. And then you have a self state, right? And this is where the memory comes in for LSTMs, right? Your self state is sort of like a flow of memory that you have, sort of flowing through your module from the previous instance, right? So in this case, it was your previous time step, and you have a flow of memory. It's just a tensor, right, that you add and subtract to, that is also connected to your current module. And that's what really makes LSTMs different, is that they have this memory that they keep in the module, that over each time step you add to that memory, you subtract from that memory, and then you manipulate it so that that memory has information from previous time steps. So let's get into the different gates that LSTMs have. And gates are just a way to sort of structure your LSTM into different sections, right? They're basically just different sections of your LSTMs and how they work together. One of the sections that we have, one of the gates, is the forget gate, which takes your previous hidden state and your current input, and it says, okay, we have this previous hidden state, right? We have this previous experience that we have, and we have our current input, right? We want to somehow erase part of that hidden state to add it to the memory, because based on our experience now, there are some things that we actually don't need to have, right? And so what are those things that we don't need to have? And that's what your forget date effectively does. And what store does is it computes what information you want to add to your memory, right? So it computes what information you want to add to the experiences that you had based on the current input, the hidden state, and so on, right? And update, all this does is actually updates the memory, and then output, it's the part where we had here, where you just literally output the next cell state and output the hidden state for the next module. Yeah. And so let's start with the LSTM cell state, right? So you can sort of think about cell state as a conveyor belt that stores all the important information, all the important memory from previous time steps, right? And on each time step, the cell state is updated to forget the things that it doesn't want and to add the things that it does want based on the current experience, right? So it's sort of like this flow of memory that goes through your neural network, right? Where you add and take away anything that you want so you can use it later on. And if you guys, pay attention, if you guys were paying attention last time, you might see, you can sort of deduce why this thing right here is solving, helps the vanishing gradient problem, right? It's sort of similar to the reason why, you know, residual connections and ResNet solve the vanishing gradients problem, right? Is because it helps the gradient flow through your neural network, right? Because it helps it avoid all these complex instructions. And if you know, there's an additional pass towards your earlier node values. So you know, it helps us manage the vanishing gradients problem by helping gradient flow. So that's what your self state is. It's just a memory that you have that you let flow through your time steps. And if you guys are wondering what is this, it's just a tensor, right? That's all you're doing. You're taking a tensor, you're adding or subtracting to it over. It's just a bunch of values, just a bunch of numbers. And so to get into LSTM sections, let's start with the LSTM forget gate, right? So this is where it gets really interesting. So you have your previous hidden state, which is your previous output, right? And you have your current input, and you take these, you put them through this, concatenate them, you multiply them by a weight matrix, kind of like a B4 neural network. It's basically a B4 neural network. You add a bias to it, and then you put it to the sigmoid function, right? This way, the values of this forget gate are between 0 and 1, right? And eventually, in the next step, you're not in the forget gate, but in the next step, what you're going to do is you're going to take this vector, right, and this tensor, and you're going to multiply it by your current memory, right? So you know, you intuitively the values are going to be between 0 and 1. So if the value is, for example, 0.1, it's going to diminish some of the memory that you stored up in your self state. And if the value is 1, it's going to keep it, right? So that's why we call this forget gate, because all you can do is you can keep sort of your intuitively, this is what we think it, you know, how we visualize it, how you can think about it is intuitively, you can only keep the data you have or diminish it, right? So that's why we say we're forgetting the memory that we have. And we'll talk about how we're going to do this in the update stage. But for now, you're just taking your previous output, you're taking your current input, you're concatenating them, multiplying them by weight matrix, adding a bias, putting it in sigmoid, then that's it. This is basically a 3-4 node network with a sigmoid activation, right? That's what it is. And yeah, that's your forget gate. And then we have our store and input gate, which is also really, really interesting. So now we have our concatenated, you know, previous output and current input. And then we take these and then we put them through 2 neural networks, right? And then we say, okay, based on the current experiences we have, what are the things that we want to update to the memory, right? So now we're not dealing with forgetting anymore. We're dealing with new experiences that we want to add to our memory. And all that you do is that you concatenate them, put them to one neural network with a sigmoid activation, one neural network with hyperbolic tangent activation, which makes the values, pushes the value between negative and 1 and 1, so that you have much more flexibility. And we just multiply them together, and later we'll add them. But this stage is for the update. Right now, we're just talking about the stored input. So this is where you want to store new information, new experiences that you've had. And then our next stage, we have our update stage, right? But before we get into this, does anyone have any questions on this? Does it make sense? Yep.
So the difference in forget and store gates is like they have the same inputs into them. It's just that they have different weight matrices, because you have like a WF for forget, and then you have WI and C here for store and input.
Yep, exactly. Like in the case of your, in the case of your forget, you have a separate weight matrix, right? So these are the learnable boundaries, and this is separate from your store matrices. So they're separate matrices. And this also does add flexibility because you have a hyperbolic tangent over here, right? Which means that the values are much more, the range is a little bit more because you have negative values, you have positive values, and so you can have more complex data that you can add to your self state. Yeah.
I guess my question is just, wouldn't the hyperbolic tangent in this case also screw up the gradient learning thing? Like I know we have this like gradient bus that's just going all the way through, but it's like almost like arbitrarily limiting the magnitude of like what we can store, right? Like why hyperbolic tangents?
Yeah, that's a really, really good question. I have to come back to you on that. I'll have to come back to you. because I've actually asked this like to ChatGPT. I was like, why do you have to have all tangent? Then I also Googled it, not to say ChatGPT is sometimes a good source. So I've actually Googled and from my research, pseudo research, one of the main reasons is because hyperbolic tangent also has negative values, but I'm not gonna act like I know it. I'll research and come back to you guys on that one. Yeah. Does anyone else have any questions?
I think even one of the circuit itself is like first proposed in like 1997, and like they like adopted it to just like there was this one like electronic engineering paper or like neural computation paper that proposed it, and I think they like try to like modify or like try to model after that, and maybe it's like they're like, oh, like they use like a 10H sort of thing. Let's use it too.
It's just that way because it is.
Yeah,
Embedded.
there's a reason why transformer completes with everything after that.
Because it's so that's a good point. Like, why would you have hyperbolic tangent? Because it like sort of like it constricts the range. Because if you have a higher range, you can actually manipulate your cell memory more too.
Yeah.
So yeah, it's kind of like, why would you do it? That's a good question. Yep. And to go into the next section, we just have our update. All we're doing in this case is just we're taking our store value, right? We're taking the two enters we have here, we're multiplying them together. And by the way, this multiplication, right, you're gonna get the same tensor at the end. All you're doing is you're just taking element-wise product, and then that will be the next value. You're not doing a dot product or anything like this. You're just taking, you're taking every value of the matrix and you're multiplying them together. That would be your next. Yeah, that would be your next value. And specifically, all we're doing in the update stage is we're just taking our store, we're adding it to our cell states so that we have new memories, right? We're adding the new memories that we have. And then for the forget stage, we're multiplying it by our previous cell state so that we diminish or keep the memories that we want to keep, right? So that's all that's happening in this case. And also note that the trainable parameters are shared across all time steps. The way we train them is a technique called back propagation through time. We're just unfolding the network through time. So this is still an RNN, guys. Yeah. Does anyone have any questions on this? Any questions? All right. So LSTM gates. This is the output gates. So this is effectively as it says, we're just outputting a value to the next time step, right? So it's the same module, but just over an X time step. So now we take our our hidden state, we take our input, and concatenate them, we put them in another sigmoid, right? We take our, we take the memories that we have, our new updated self state, and then we put it for hyperbolic tangent for some reason, and we just multiply them, and that will be our next hidden state, and it will be also our output, right? So, if you reach the end of your time step, this will be your output. So effectively what you're doing is you're taking your current experience, and then based on the memories of the past, you're saying, okay, this is what, this is my judgment, right? So I have all this memory from previous experiences. I have my current inputs, and then I can deduce what the output that I need to be. And that's sort of like a brief sort of intuitive sense of what's going on here. Yeah.
In this case, what exactly is the output? Like, are we trying, like, if say we're trying to predict what the next word is, do we only care about the output of the very last word right before we do the prediction? Or like, are we also in the middle trying to predict what the next word would be? So we're just doing like a bunch of word prediction all at once? Like, or is that just more problem dependent?
That's a really good question. So again, it is problem dependent because technically the LSTM actually outputs every single time you put in a word.
Yeah.
Every single time you put in a word, it outputs it. So for example, if the keys, let's say you have a piece of text, right? And you want to classify the text based on sentiment, right? You would take only the final hidden state value as your classification, right? But if you want to generate words, for example, you might not take only the final hidden state value. You might also take the intermediate outputs of your LSTMs, which actually brings us into another problem. As you have sort of this limited context window, right? Where you have the initial time step, you have the next one, you have the one after the other. If you're for some reason, taking into account your initial hidden states, those might be based on a smaller context window and so on. But like to answer your question, it matters what context you're looking into it. If it's correct classification, you only consider the final output. If not, you might consider previous hidden states as well. It's based on, what situation you're in. An LSTM summary. So just to give you guys a brief overview, LSTM is a type of RNN, and it incorporates something called a self-state, a memory, to which we add, we subtract, and we use that memory to make future judgments, right? It solves to a certain extent a big problem that we had with RNNs, which is just the vanishing gradient problem, and also understanding long-term dependencies a little bit better because of the self-state, because the self-state has information from previous time modules, from previous timestamps. And so yeah, that's a brief summary of LSTM. Does anyone have any questions on this? All right. And coming to the big part, transformers.
Well, waiting.
Okay, I resume slowly.
Oh, where are we? Okay, we're here. Good, everything good? Yeah,
Clicking X out of the big screen on the side.
here?
Yeah.
Oh, I can just, whoa, that's weird.
I know.
Okay. Yeah, it's good. Okay, wait, why is my things, whatever. Okay, transformers, yeah. This is the stuff. So this is kind of like the backbone to like all of the things that are cool these days, which is like all the image stuff and all the text generation stuff and all the cool stuff. Okay, great. So a little bit of a history lesson. This is a little bit of how transformers, kind of where the idea came from. So there's these things. So we had RNNs, right? We just went over that, LSTMs, right? But the main problem with RNNs was this thing of we had to like pass a hidden state along as we were encoding a sentence or doing something with it. And the problem is, if that hidden representation or the hidden state is a fixed size, no matter what we do, it's not at a certain length, it's not going to be able to encode the entire representation of the sequence so far. And that's kind of annoying. So what they came up with is something called an attention mechanism in RNNs. And the idea was that when you were decoding, you allowed it to actually look at every single generated hidden state that the RNN produced, and then it could actually choose. Wait, do I have a next slide? Yeah, it could actually choose which one of them to use. So, it goes this one. So yeah, like let's say you're at the very last hidden state, it didn't have to have the entire sentence encoded in this one hidden state that gets passed along. What we could do is have it so when it's decoding this single word, let's say this is like translation from like English to like French, when it's decoding that one word, it can actually figure out what words it wants instead of having to, again, have all the compression go in a single state. And this eliminates the problem of small memory constraints. Again, this is going to cost more compute because you're going to have every single one encoded and then choose between, but it does solve our issue of long-term memory problems. So yeah, that's pretty much what I said. That's what the mechanism looks like. It pretty much just takes in all the previous hidden states and the current output hidden state, and then passes them both, and then it aggregates them, and then it outputs a signal, which is this. So the main idea you can think about it is like, here is like us asking what is, like, we want something to be relevant to what I'm going to generate, and then here are all the relevant things, and then it combines them and picks the hidden states out, and then passes that to the decoding step. A little intuition there.
So that's like the LSTM, like forget state, or like the store state, where it's like it does a softmax thing and says which one is important, which is not.
But it does it when it's generating. It doesn't have it so it has to compress it. It does it every single time. It looks at all of them, says, what do I want to remember? What do I want to forget? Yeah. So yeah, what's cool is actually you can see how one decoding state, so this is the encoding, this is the English sentence, right? And then normally you'd run through with an RNN encoding the sentence into a vector hidden state, and then you run another RNN that would go here and try producing the decoding, right? But with this attention mechanism, what you can actually see is in the decoding state, again, we allowed like one word here to look at every word and pick what it wants to look at. And we can actually visualize the magnitude of the strength. And we can see this word, like it looked most likely at this word, which is signed. That's seen, I don't know how to say that. I don't know how to speak French. But what's cool is you can actually see that sometimes when languages swap words and things, the actual magnitude of the attention scores between the input words and the output words actually correlate. You can see where it's actually getting this decoding step information from. It's looking at this word. right? So like European Economic Area, zone probably responds to, yeah, zone means area, and then you can see how it like flipped all the words, right? And you can actually see why it produced this word here by looking at which word it intended to. So it's pretty cool. You can actually visualize this, right? So attention is all you need. That was a little recap, RNNs. Attention is all you need. Why is it called attention is all you need? This is the transformer paper. This is the whole architecture that means everything, right? And yeah, so let's just go here. Yeah, I'll skip to this. Anyways, this has an insane amount of citations. This came out in 2017. That's like 96,000 citations, which is like crazy. That's the architecture. We'll explain in a bit. But the main idea is attention is all you need. What do they mean attention is all you need? Well, this step right here, over here, is done sequentially, right? Remember, it's an RNN. We're running over the sequence. And while we do have this kind of attention where the decoding steps attend to the encoding words, they said, wait, why are we still processing this sequentially? What happens if we could just do this attention thing, but have the sentence attend to itself? Whoa, cool idea. This is called self-attention, and this is, again, why the paper is called Attention is All You Need, because they're saying we're going to get rid of this recurrent structure of this RNN producing, and we're saying, wait, if we already have this attention mechanism from the decoding step to the encoding step, why can't we just use that for the encoding as well, and then everything can be parallelized? So yeah, just apply attention to itself, like apply attention to the sentence itself, aka self-attention. So real fast, just a RNN comparison and a reminder, right? We have a sentence, we can encode the sentence by passing it through an RNN, and then we can grab the final output hidden state, and then we can use that hidden state to then decode a sentence, right? And again, we can apply an attention mechanism where we have this decoding state, actually be able to look at every single one of these hidden states. But for now, again, general idea, you have this part that encodes the sentence or thing, and then it can decode it, right? But can we do different things besides that one combination? And yes, we can. So there's a bunch of different ways to use these kind of modules. We've been doing many-to-many so far. This is like a sequence-to-sequence task, which is like translation. Because think about it, you have a sentence in, like a couple words, and then you want to decode a couple words. You can also do many-to-one. Many-to-one would say, I have a sentence, and then what I care is the output, is this saying something nice or something bad, right? Sentiment analysis, like is this a positive review for a movie or negative review? It's not like you want it to then generate like a summary that would be this. This many-to-one is normally just using the encoder, which just tries to compress the sentence into a single representation, which is used at the end, and they just classify on that. So just real comparison, looking back at this, we can encode the sentence, I love learning, and we can have this go to two outputs, positive or negatives, right? And that's kind of the idea with that. The last one is another one. It's one-to-many. So one-to-many, you can use this for generation. This is actually what GPT is. It's just the decoder part, right? So it just starts at some embedding and it just starts generating, decoding, and just outputting stuff. So again, this is like the decoder, right? Where it generates stuff. This is the encoder where it compresses and encodes it. And you're gonna see this is an encoder because it encodes the sentence and then it decodes it, right? So general just kind of reminder. So this is transformers. The transformer, I broke it down from earlier. I'll skip back to that slide actually just to show. This part is the encoder. This encodes and then this decodes, right? So the original architecture is meant for sequence-to-sequence tasks, right? Where you're going and you are encoding it and decoding it. And again, that's a many-to-many. But in practice, like these days, a lot of times we just use an encoder or decoder. We don't really opt for both. There's some papers and things using it, and you can't do generation with both. But the main idea is that we can actually just use an encoder or decoder. And I'll just go over popular encoder first, and then we'll go over decoders. So BERT, this is a transformer encoder, right? I'll get to architecture a bit later, but right now I'm just going to explain a transformer encoder that's really cool. This is called BERT. It's a transformer encoder. It's made by Google, right? And it's, again, just the encoder. And again, what do encoders do? They encode stuff. So you give it a sentence, and it turns it into a single vector, and it can be used to classify spam, not spam. To be honest, they probably use this on Gmail, just to look at it, and they probably can classify it and just say spam, not spam. And again, it works by the same idea. You have this input, this sentence, you compress it to a vector, and then you from that you can use it to classify it, right? Again, this is the many-to-one task. Yeah, question?
So in creating that output vector, what is being attended to? Is it the letter token or the word tokens? All the word tokens come in and they can self-attend to each other?
They can self-attend to each other. I'm gonna explain that in a bit.
Amazing.
I'm just holding off architecture right now.
Fantastic.
I'll explain it in the decoding, yeah. So yeah, we're just trying to encode a sentence. This is BERT. Cool. Again, each of these hidden states, like we just use one of the hidden states, which is like pretty much, just ignore that it's there. Pretty much, again, the end hidden state, which is encoding the entire sentence, and we can use that to classify it. But we can do more than that. We can use, once we use the individual word hidden states, right? So what we can do is actually, just like an RNN, how it each time it had a hidden state, we have each of these hidden states actually used to like label words, right? This is called tagging a sequence of words, and this looks like this, right? So we can have it so after each word's processed, we then have its hidden state outputted, and we can actually have that go through a layer to classify. So we're not just taking the whole sequence and classifying it. We can actually classify each of the hidden states, and we can use that for like sequence tagging. Yeah, so this is called like named entity recognition. Just another cool thing you can do with just the encoder. So how does it learn to do this kind of enriching, right? It pretty much just does exactly what Jordan was talking about earlier, where again, this is the same thing as an RNN. Just I'm explaining it with how BERT does it. So you can blank out a word, right? And then what it does is we say, here's the original sentence, we blank out a word, and then what we do is we take that guy's hidden state and we say, try to predict the word that is missing there, right? And then we just keep doing that over and over, or we blank out a word, we say, you have to encode the rest of the sentence and have it mix into this vector to produce a really rich hidden state that is good enough to predict that word, right? And that is what enables us to do these really cool tasks, right? Like if we didn't have this training objective that was good enough to capture meaning of like a sentence, then we couldn't use this little hidden state to classify what the sentence was about. We couldn't use it to tag the words. We couldn't do any of that. How we're able to get the model to get these really rich vectors that we can do and process afterwards is through this training objective of fill in the blank. And it works surprisingly very well. Yeah, so yeah, that's another thing that doesn't really, we can skip that. That's another training task. But BERT summary, it's called BERT for bidirectional in that it attends to the words on either side of it. Encoder, because it encodes. Representations, because it encodes vector representations. And then transformer, because it's transformer. So BERT stands for bidirectional encoder representation transformer. That's the paper name. Yes, Oliver.
Is the bidirectional important? I thought attention was like every vector to every other.
So yeah, in the encoder, we are looking at everything from either side, right? Yeah. So no, it's transformer encoder. It's any encoder specific, right? I'm not sure if I have a slide for it actually. Yeah, but yes, BERT, it can look at all the tokens at once, right? Because it's not really generating anything. It can intake all of them, and we allow it so like the center word can look at the future words and the past words, right? Because it's just trying to capture the meaning, right? But if it was trying to generate, we wouldn't allow it to look at the future words and attend to them, because then when it's actually running, it doesn't have those, and then it would mess up, right? So I think I'll explain more. I think it'll be good when I get to the parallel of the decoder. I think they'll help. So yeah, anyway, BERT, this is really cool. Google, again, made the transformer architecture, which OpenAI and all these ChatGPT is constructed by in 2017. And whatever, that's fine. This is the main thing, though. BERT was deployed in 2019. If you use Google search before October 2019, you might have had results that were literally like this, where it says, like, let's say you Google, can you get medicine for someone's pharmacy, right? And it would just give you like, okay, I think it would probably just do like word matching or something. And it would say like, okay, they want like medicine and they want like pharmacy, right? But BERT is so good at encoding a sentence into this rich representation that they can compare that to websites, and it's rich enough that they can actually understand you want to get have a family. You can get this for some pharmacy. They understand, the model is able to understand that you want it for a friend to pick up the prescription for you, right? Because that's pretty hard from that sentence, just thinking about the word frequencies, because most of the time you think about pharmacy, medicine, that's gonna come up with a result that is just about the prescription, right? But to understand the semantics of a sentence really well, this task of just having it predict a blank word actually makes it so that vector that it produces at the end has a really rich representation and embedding that can be used for this task of website comparison even. And yeah, they adopted it in 2019. You can look at that. It's pretty cool.
So they just like go around with like a bunch of the popular websites, just start burning every single one of them with like they have like a encoding for every single one of them, and they go, okay, cool.
I think they
And then we just
do.
start comparing them.
I think they do semantic similar. Yeah, I
Yeah.
think they do the normal algorithm of PageRank and all that, and they grab their top 100 websites that come up, and then they go on each of those 100 websites and they grab like chunks of the sentences or paragraphs, and they encode those into vectors, and then they encode your search into a vector, and they figure out which one of those vectors is closest to your vector, your embedding. And because this embedding is so rich in representation, the closer they are in that 300-dimensional space, it actually says like they're closer in meaning. Just like our words, right? The words in our word embeddings that were closer, they're closer in word meaning. After these tokens are processed, that end thing that we use to classify, right? This end token that we use to classify, just like in the RNN. Let's go back to do. Oh. I just want to, whoa. Oh, oh my God. How many? Okay, there you go. Way too far. I went way too far. This thing is rich enough to like do that kind of representation in vector space. That's the main idea, right? This encoded representation that we get from capturing a sentence is rich enough to do that. Again, same thing here. It's rich enough as well. The encoded representation of a sentence is rich enough to do a translation in the sentence to another language, right? If it wasn't, it couldn't produce that sentence, right? So again, this encoding is super duper rich, and we can literally just throw on a linear layer to have it predict something. And the reason why is because this is an emergent property of having it pretty much fill in the blank, right? Just by having it fill in this blank, it feels a little bit like magic. But just having it try to fill in the blank allows whatever this produces to be really rich. Because think about how complicated the task of actually filling the blank is. You need to understand a lot of things. If you can do filling the blank really, really well, that means you understand language actually really, really well, which means that vector, that representation has a lot of meaning. Just trying to hone in that fact. So yeah, that's BERT. BERT's cool. It runs pretty much every time you do a Google search. Really cool. Okay, we're gonna get to GPTs and OpenAI. So GPT is simpler, even simpler than BERT. It's gonna be way easier than BERT, to be honest, training wise. So instead of using just the encoder, which is this guy and this guy, to encode a sentence in a single vector and use that, we're gonna do, remember, the decoder. And the decoder can be used for actually, once we have it hidden, we can generate the output sentence. Again, maybe the encoder, we can encode a sentence, and the decoder, we can decode a sentence in another language. But what we're gonna do is we're just gonna use the decoder. And if you're just using a decoder and you're not starting with any hidden representation, you can think of that as just generating, right? So the decoder is like a generator. And this is what GPT is. It stands for, do I say it? Oh, let me see, wait. I don't say it. Okay, well, I don't say it, but it stands for generative pre-trained transformer. That's what GPT stands for. It's generative in that it's it generates, it's pre-trained, not just trains, and transformed, right? So it's just the transformer decoder, and the idea is that the decoder again is doing that generation task. And just like BERT, what is our objective? What is our training objective that lets it capture a rich representation of the sentence so far so it can predict the next word? How does it get that really rich representation? It, instead of doing fill in the blank, it kind of does fill in the blank, but it's fill in the next word, predict the next word. And that's the task we train it on. So this is a decoder. We give it a sentence so far, and we pass it in, it produces an output, and that output right there should be able to be the next word in the sentence. So how we train it is we give it a full sentence and we say, get rid of the last word, right? And we say, give it all the sentence so far, I want you to predict the next word. And again, it feels kind of magical that literally just by doing this, we can get it to, when I say, hey, generate this or do this code for me, it can actually understand that. It feels super weird, but this training objective has a really powerful, like, emergent properties that is pretty much how it works. Yes.
I have a question about how it understands that, because as I see it, it's just predicting the next word. So that doesn't really mean it's understanding it, because it doesn't really know what that word is.
Doesn't understand what? Sorry?
So I don't think it's like really understanding it, because I may be wrong, but like that's how I see it, right? So I don't think it's really understanding the meaning of like the word that it's outputting, but it's just basically like predicting which word fits in best after this particular word, right?
Yeah.
And therefore it's basically just predicting words.
Yes, but
Which do end up making sense because of the data it's been trained on, which makes sense to us, right? So therefore it makes sense.
I agree that
But what's the philosophical difference between understanding and outputting the next word?
yeah.
Like, what are we talking about really? If you can perfectly out the next word, like that is understanding, isn't it?
No, but in this case, it's just like predicting the next word. It's not quite understanding, because it's never going to deviate from the data it's been trained on, right?
Well,
I mean-
if there's enough noise in the data and it encounters a new thing, a new sentence, statement it's never
Right.
encountered before, it'll do based on the meanings that it's intuited. In that case, it's generating.
No, but that's still not the meaning, because it's still based on the data that it's been trained on. So it's just predicting what would come next.
I
It's
love
like a
it.
step back to
Obviously.
we can go like embeddings. Embeddings capture meaning, right? We agree embeddings.
I was just gonna make a different point, though, which is that like I can have a GPT-4 instance and feed it a library that didn't exist during training, and it can infer enough to like help me write code using that library, right?
Yeah.
So you run into these really nebulous definitions of what exactly is an out of distribution sample, you know,
Like this is the whole like OpenAI approach, which is that if you give a model enough data, and this data is so big that it is able to almost perfectly sample what we think this like nebulous distribution of what all possible human language is, then eventually, as the model has seen so much and is able to predict so much, it must have kind of like understood enough about the task of predicting the next word that internally it must be able to capture meaning of the sentence. Like this doesn't just stop with large language models either. We're going to talk more about this and like I think the next workshop, which is with like large vision models in general.
Right.
Like last time we talked about like ResNets and LSTMs and stuff like that, right? What people found is that with these ResNets, you can do something called transfer learning, which is you just take these really large models, which was the ResNet was originally meant to classify the ImageNet data, which is only 1,000 classes, right? You can take an image that's like completely out of distribution for like the original data sets. Like it's not one of any of these 1,000 classes. And what we can do is say you have a different data sets that's like a different set of classes, pass these image through the ResNets, and instead of doing that very last layer with the classification, we just do one layer before that. We take that 4,096 dimensional vector, which is actually our embedding of the image,
Right.
and just train another classifier based on that to do some other classification task. So like in a lot of machine learning, one of the things that people have found is that if you train a big network on enough data, its internal representations must capture enough information about the thing that you have passed in, such that you can use it for downstream tasks and use it for other things. And then, like obviously understanding is a very big word that we've been throwing around, and it's, something that we don't really have a great definition for, but we use the word understanding because it is able to, most importantly, generalize.
So an
Yeah.
example I'm gonna give that I think might help kind of relate it's kind of hard to bridge the gap between us learning and it learning, but think about this. Let's say you're doing a test and there's a bunch of questions, and for you, let's say you want to write the right answer, right? If you write the right answer, like for some physics problem, to actually do that really well and get the correct answer, you needed to understand it, no? There's no way you're gonna just write the answer to the physics problem of the car is going this fast, whatever, without understanding it. It would be impossible if the model didn't have some internal understanding of like physics and something to be able to predict the next word. Think how hard it would to predict the next word of, okay, the ball is going this fast and going this side. The Jimmy is like here and he's falling, like the relative speed is this. And then how fast is he going? Right?
To like give a counter side, like let's say you train it on Chegg, right?
Yeah.
Chegg has so many physics problems already with the answers to it.
Yeah.
Like if you have a human who can like remember every Chegg question with the answer to it, I'm sure he could like figure it out. And like, because it's basically after that, it's like basically recalling that particular Chegg question, which I'm sure it's doing
Yeah.
internally.
So here's the thing though. We can now, this is why we have test data in training. We can now give it, train it, give it an example it's never seen before. And that's the real power of machine learning, is that from the learning distribution, the training data, it can generalize to an unseen example,
Yeah.
right? And that's the main idea. This is just on a larger, insanely more scaled level.
Yeah.
Yeah.
The last thing is, the last thing is there's a fun experiment called the Chinese room. Read that. It captures the essence of what it is to know something versus not know something, and how it almost doesn't matter in cases like this.
And there's another thing, which is like, Anthropic has done some really good research, I think it was them, on like interpretability of LLMs and how you can sort of look at the internal weights and see like how it's sort of discovered concepts of like honesty and.
That is last reading group. If you go look at that was mechanistic interpretability by Will, who pulled a bunch of stuff around there.
Talked for like 2 hours about all this, like, oh wait, Transform actually does understand things because when passing, I think stuff actually like something actually look at and be like, oh, it does. It's actually capturing really important information about things it's never seen before. So take a look at that.
There is a good point though to be said of when it's tricking you to thinking that it does have that internal representation versus its fed data. One example they give is like, let's say something is bigger and this sphere is bigger than this like pyramid, right? The thing is, if you then swap the order, it will actually think like this one object can fit into the other even though it can't. So a lot of the times how people like to phrase questions is in the certain large, small ordering or something like that. And there's an inductive bias where it'll most likely get it right and you think it's always right, but that's just how it's fed. So the testing examples we give are very important to understanding, does it actually have an internal representation or is it just going off a probability distribution? So there is like a in between. Yeah. So just real fast to go off that, I'm skipping ahead a little bit. For reference though, like the scale of these models is insane. Like this is BERT. This is BERT. This is the encoder that is run every time. Remember we talked about this? 0.34 billion parameters, which is like really small, right? That is like what, like less than it's not even a gigabyte, I think. Is it? Is it 4 times 4? Yeah, it's a gigabyte. Yeah, quantization. So that's crazy. This is GPT-2, right? Is 1.5 billion parameters. This is GPT-3. It's 175 billion parameters. GPT-4 is probably like even more massive, other things. But again, the amount of data and the amount of money they spent on this, this is the main thing I'm trying to say though. 570 gigabytes of text that's filtered from 45 terabytes of text. Like imagine writing a text file and getting it to like a kilobyte. This is like a 570 gigabytes. It's just like the amount of data they get is insane. And again, this is like the amount of tokens and data distribution. So it is a lot, like so much text. Like it's like you need one of those like zooming out videos to understand how much text there is. But
concerningly large amount of data.
yeah, no, that's maybe why without fine-tuned, it's a little controversial. So back to this though, we're actually going to explain the architecture because that's pretty important to understand.
As somebody mentioned that there is a 4chan GPT that someone at some point trained. It was so out of pocket that they had to be taken down because people were like, oh my god, this thing is saying just the most heinous shit. But yeah, that's the thing that exists.
So yeah, GPT is just the decoder, right? And it's trained on this task of predicting the next word, right? Given the sentence so far, generate the next word, right? So this is the whole deal. I'm gonna explain transformers, just pretty much the decoding part, because that's pretty much what most people care about, which is how ChatGPT works. And it's pretty transferable. So let's get into it. Okay, this is this is like a little more math heavy, a little more understanding, but this is really the backbone of a lot of stuff. So this is the steps we're gonna do. Okay, this is the architecture right here. A little intimidating. I'm gonna break it down. Okay, we first got step 1, tokenization embedding. We learned this. We just learned this. So that's the first step, right? Second step, something new. We're gonna add something called positional embeddings, right? Third step, we're going to do this self-attention thing where the sentence attends to itself and then uses that to produce, right? Then we're going to do a feed forward The feed forward is gonna actually, we're not just gonna do one kind of attention attending, we're gonna do a bunch of different kinds of attending. And then we're gonna combine all those predictions of different ways to attend into a single vector, and that's new sequence is gonna be used to attend a bunch of times, and we're gonna repeat. So we're gonna repeat 3 and 4, steps 3 and 4, n number of times, and these are the number of layers, right? So each block or layer is gonna be comprised of this mass multi-head self-attention and a feed forward, and that's what this is here. And then you just pretty much repeat that block n times. That's what the architecture does. Again, there's these things, those are called skip connections, you look into them, and it just normalizes. So again, you don't really have to worry about those, just little implementation details. Even though the skip connections are probably the most important thing about it and doesn't learn without it. Anywho, last step, we finally process these tokens. We have these lists of tokens, we process them, we combine them, we did this thing, we produced them a bunch of times. And then at the very end, we get our final token, again, the hidden state for each of our words. And we have that, and we pass that through, again, the softmax, linear softmax classifier, like prediction. And it pretty much just projects that vector into the dimensional space of 50,000, because that's the number of words we have. And whichever dimension has the most, largest magnitude, we say that's the word predicted. And then we back propagate so that it tries to increase the magnitude of the dimension that corresponds to the correct next predicted word. That's a lot. We're gonna break it down very slow. So I think we already did this tokenization. This is actually, you can go look at that tokenization. This is how GPT-3, its tokenizer actually works. This is how it breaks it down. Kind of cool. And you can see the number. Yes, Oliver.
Oh, sorry, yeah. I was just gonna say, like, so are there like preset like tokenization stuff, like how there's preset like tokenization algorithms, like how there's pre-existing like
Word embeddings, you think?
sure, like if someone wanted to make like a transform architecture or whatever
Yeah.
themselves, they could just pool like another person's like big database of words, characters, and their corresponding tokens and whatever.
Yes.
I spent all summer doing
Yes,
this.
yeah, yeah.
Yes. Yeah, so there's the what's the OpenAI tokenizer Python library called? TikToken? TikToken. A library called TikToken. It downloads what's called BPE, which is byte pair
Yep.
embedding. It downloads those model files, which are they're not like real. It's like, you know how like state vector machines or whatever are machine learning. It's that kind of machine learning. And it does that. And there's a million algorithms, and you can spend an entire summer on this
Yeah.
if you get stuck.
Yeah.
So there's a fixed way of doing it.
In fact, LSTMs, the very original paper, proposed it as a state vector machine. Anyway.
Yeah, so you can break them down. You can have a fixed scheme of doing it. I can explain by pair coding real fast. It's pretty easy. You just look. So you first start with all the letters and all the characters possible. You usually have a list of every single letter possible, right? And then what you do is you then look through all of your documents. You say what two letters follow each other the most, right? And you find the frequency. And you're like, maybe it's like T then H. That might be right. And then what you do is you add T and H as a token into your list of tokens. And then from there you say, okay, which letters follow the most, right? And then probably two other letters, and but then at a point, once you add the list, it might be TH and then another one of those. And you keep doing that. So what happens is, let's say you go up to 50,000 till this list reaches 50,000. You now have 50,000, and it's like, why did you use these as tokens? Well, they're the 50,000 most common things that appear after each other. So it's probably most efficient to encode them into a vector, right? So that's how we choose how to do it. It's by pair coding. It's pretty easy. That's it.
And fun fact, zip compression works in a very similar way, but just on like the byte level.
Yeah. So yeah, we tokenize, we embed. This is cool. I love looking like it's so cool. It's so cool. So that's step one, right? We split it up into these like things that we can then we're going to process, right? And then they're not just like numbers, they're like vectors. So these are vectors that we're going to process and do stuff to make a really rich vector. So again, the problem though with this transformer architecture is this kind of self-attention thing where they all look at each other. The problem is when they look at each other, there's no there's no bias, there's no temporal bias of this one came before the other one. Because when you're actually running an RNN, the word coming in gets processed by this network, and it actually knows that this is the later word. So how it gets added might have an actual bias of saying, hey, I'm the new guy, and the old memory is like, I'm the old information. So it has a bias of how it actually, things are related spatially. In transformers though, there is none of that sequential processing. It all happens at once. So it's hard for it to actually know what what the order is of anything. There's no information of any of these tokens or anything inductive of the model that tells it what the order of things are, right? And this is similar to kind of, if you think of like a dense network versus a CNN, right? A dense network has to learn which pixels are next to each other. You flatten an image and then you have that to a dense network. It doesn't, the weights don't know these three were next to each other, these weren't. But a CNN, because of the architecture, it has there's a spatial bias that through the architecture, it knows these things are grouped together because you force it to process them together. Same thing here. RNNs have a temporal bias, but transformers don't. So we need some way to inform and tell the transformer what order are these things in, right? So this is where comes positional embedding. We pretty much we have our word, we get our word embedding, and then what we do is we add a positional embedding, right? And this is another vector that encodes where it is in the sentence. So the first vector, for example, let's say it's like, how are you doing? How and are and you will all get completely different positional embedding, right? The first one will be added with a positional encoding of 1, and then 2, and then 3. And again, they're not just numbers. These are going to be vectors that, again, also have rich spatial meaning, and that can actually encode position. So this, like word vector, they have spatial meaning, right? Like if you add one to another, queen and king, all that stuff. But the positional, when added to the word vector, it actually can move like the word the to be like the first sentence is the beginning of the sentence is the, right? And it actually, what we try to do is this positional encoding, this embedding, we try to make it so that it doesn't ruin the semantic and spatial dimension that these word vectors exist in, but nudges them slightly in a way that it can differentiate them and say where they are in the sentence. So it's a kind of hard task, but you can do this through a learn process where it just learns like what the encoding of position 1, 2, and 3 and all that is, or you can actually just use a Fourier kind of like decomposition thing where the first values of the position of a high frequency wave, then a lower, then a lower, then lower, or sorry, other way, low frequency, then higher, higher, higher. And that vector is actually rich enough to encode good spatial meaning. And when you add it with the word vector, it actually gives you this really cool embedding with positional context. So it's like this vector that can represent a word, but also like where that word is in a sentence, which is kind of cool, which is necessary. Yeah. I think it looks, I got rid of it, but what am I looking? This, you know.
Also, another thing is, this is confusing. It's because it's kind of arbitrary. Like you read the paper and just like they're like, yeah, we use this as a position embedding. It's like a sign and a cost. You're like, what?
This is kind of what they look like ish. Like imagine you grab this row right here. This is position 1. That's vector. This is position 2 vector. This is 3. This is 4. This is 5. This is 6. Right. Yeah. So the idea is if I give you one of these columns, you could uniquely identify it. Right. Maybe this guy. Look, this guy's column is the same as this guy. But if you look down here, the high frequency wave, it's a different position than this other guy. Right. Yeah. And that's going to kind of, again, this is like Fourier decomposition. So you can reconstruct a signal. Right. It's kind of that with position, but it gives it a richer thing to actually manipulate than just a number, right? Because that's not really good for it, like mathematically and how it operates. Like 5 versus 4, that doesn't give me like 5/4 is how I translate from one position to another. That's really hard versus just multiplying a frequency by 2, right? So it's kind of nice. Fourier is really good for this. Again, decomposition.
You actually realize that in again future workshops when we talk about this is whenever you want to somehow input a number, that's like a 1 to 10 sort of thing, like some sort of positional thing. People use Fourier a lot. That's just something we use a lot, and then like in stuff like nerves and stuff we're talking about.
Yeah, really, really good. It's like
So anytime you're trying to input like straight up any number, this is useful.
yes.
Like, because you either need to one hot it or you need to do this, and sometimes one hotting doesn't. Like you wouldn't
one hotting. It would actually just be the first layer would just convert it into that vector. Does that make sense? It would pretty much like one hot. It's kind of like if you pass that through a neural net, the next layer is like what that one hotting turns into.
Yeah. Okay.
So it's like kind of same, yeah. But again, it's hard for it to learn this really good thing, and we know it's already really good, right? It's kind of like a kernel method. Is that what they're called? Kernel functions? No. Okay, whatever.
You can model it as that.
It's fine. Yeah.
Stuff.
Yes.
vector is also it's like the original token embedding.
Yes.
Has it been modified yet? or
Nope.
no?
Nope.
Yeah.
Again, these two things can be learned. One of them can be learned. They found that doing Fourier versus a learned positional didn't really change it too much. I don't know if they looked into if it learned Fourier. I don't know, but
I was thinking the word vector, that's one hot, right? That's a one.
oh
hot
no,
word
this
vector,
is
or-
the embedding.
That's the embedding.
that's
right?
embedding, yeah.
It's a word to vector.
Yes, word to back embedding. Yeah,
Okay, cool.
I have a question.
Yeah.
Doesn't the embedding already have spatial understanding?
it does. What do you mean spatial?
Like the
Like
word
as
vector?
opposed to like the other words in the English language, it knows where
It has semantic
yes, semantic.
understanding in the vector space. But let's say I have the like don't in the beginning versus don't at the end,
Right.
right? It changes the meaning a lot.
So
Right.
that's why we need positional within the sentence.
Yeah, we need to encode it. RNNs, why didn't we need to do that? Because again, it processed it sequentially and that led to an inductive bias. Same thing as the CNNs, they have a bias of I'm processing them chunk-wise and I'm grouping the ones that are together. A dense network doesn't have that because it doesn't know these three are related, these three however, right? And same thing with transformer, it doesn't know whose guy came first when I'm applying attention.
Got it.
And the last question on this, the positional encoding, let's say you have a context length that's obscenely long, 128K or something.
Mhm.
Does that mean that you have to come up with a really complicated positional embedding so you can tell two neighbors apart? 'Cause I feel like at 128K, you're running into like floating point error on adjacent.
You just need a higher frequency thing, right?
Okay.
I think, well, this is exactly how, this is why we have, so like, if you want to represent, this is, not the thing. If it's 1024, I think you just need to get up to a frequency of 2048.
Is this sampling?
Yeah, this
Yeah,
it's
it's just like stuff.
yeah, there's a limit there, and
Okay.
you only need the frequencies that multiply up to it, so it's log base 2 of, something like that. Log base 2 times 2 maybe for phases, but yeah, it's dependent on that. And that's so the problem with that is if you actually train a model on, let's say only 1,000 tokens, that's all you process is, maybe text that's only up to 1,000 tokens. If you try going past it, it is very, very poor. And that's really a problem when you're training, let's say even the 100,000 context window, is that text they're giving it is kind of like also fake at the same time, because there's not like that long of documents places.
Oh, yeah.
So there's problems. They say 100,000 context window, but the thing is, at a certain point, it starts to diminish.
We don't even have that much data that has that
Long
able to
form
support
on that, so they have to do
quantitative
synthetic things and a lot of things to do training. So it's not great, right? And that's why, even though they say 100,000 contexts, at a certain length it gets bad. If you want to look at stuff, I think I mentioned it and I deleted it. A long range arena benchmark is one of the things we're trying to do with like text retrieval and like length stuff, I think, yeah.
That's something like a newish thing, which like state space model does a lot better because it's like liquid simple.
Yeah, it's the linear, I add slides with them. So,
Oh, okay.
yeah, so we now have these rich vectors that have enough information. Oh, am I even, yeah, that have enough information that the model can actually process it. So now here we are, the self-attention thing. This is like the thing. Attention is all you need. We're not doing it currently anymore. We're having the sentence apply attention, whatever that means, to itself. And then that makes it so when it produces an output, it's now done in parallel and it produces the next hidden state and it's rich enough, which is like how does this do it? Right? So what you're gonna do is let's just take a single word. So like we have a bunch of words in a sentence. Let's just focus on like one word for now. We're gonna put it through 3 different networks. We're gonna put it through query, which is and key and value network. Don't really think about what these are. These are literally just like single matrices. They don't even have a bias. They don't have a bias even. They're just transformations. Okay. Again, why? We just want the model to be able to manipulate the vectors a little bit in some way. Again, the naming scheme will explain in a bit. So you have all your tokens in the sequence. You pass each of them. The first token you pass through a query key value, and the next one query key value. Next one query key value. All of them query key value. Now for each token in embedding that has positional information and semantic, you convert into 3 different ones. Right? What are we going to do with all these pairs of 3 different ones? Right? What we're going to do is we're going to grab let's say the last word of this process. We're going to grab its query process token, and we're going to have it get this vector, and we're gonna dot product it with every single previous token's key token, right? And that's what this process is. That's the first process, right? This is the map mode, right? So we get the query, again, from one word, and then we get the key from all the other words in the sentence, and we do a map mode, which is pretty much doing a dot product. And what is this doing, like, meaning-wise? Well, if you actually look at it, if we look at the word, let's say, bank, right? What we do is when we do that map mode, when we dot them, we actually get a dot product, which is, again, like similarity score between the vectors. So we can see bank has a 42 score, again, we can normalize it with on, has a 67 with the, and has an 88 with itself. Well, what's interesting is that, look, the and bank actually has a higher number than river, right? And it might be because the is referring to the bank. I mean, the bank is referring to, like, the and bank have good, like, meaning because they're referring to each other as a, like, object or something, right? And that's kind of the idea, is that the vectors, the word embeddings, the positionally encoded word embeddings that have closer and greater dot product similarity will have greater semantic meaning. I mean, that's just how word embeddings work, right? But what we do is, okay, we scale it, we normalize it. Okay, great. Now these all out to whatever. But the idea is this is called the attention matrix. And the idea is just like before with the weighted connections with the encoded, the translation task with the attention RNN, the lines showing weights. This shows the same thing. Again, I could draw it out. But on a sentence itself, it has how much a word relates to another word, right? So again, look, this is the same sentence. It's not like you have a translated sentence and the input sentence. We have the same sentence as the input and the output that it's attending to itself. So let's say we look at a single word. This is a query word, it, right? We can see its strength to all other words. And you actually see, look, it attends to the animal, which is kind of cool at these deeper layers, like layer 5. Because this attention head is showing us, this is probably like capturing like objects and like what they're referring to. And the word it has a strong self-attention score with the other ones. Again, if you just did the it word vector and the animal word vectors, it might not get you that really good score. But because we first passed it through this, we passed it each through these query key value networks. It allows the network to learn how to modify the query in a way and modify the keys in a way that they can match up to the things that matter the most, right? Any questions? Okay. So yeah, stop that, whatever, normalize it. Okay, yeah. So it's a nice, okay, this is a little thing. And yeah, they're a nice intuition, but at the same time, they can be deceived. So don't always, like, this is, the models aren't always interpretable as an, oh, that means it's caring about that. It's really hard to understand. This is a very cherry-picked example, so just know that. But then what do? We have all these scores, right? So like, again, we have this last word, and we have how much it matters to all the previous words, and we have like a score that each one of them have, right? So the first word, let's say it got a really low score. Or is this low, or I'll say this is low, I'll say this is high. So like, let's say maybe the first word had like an okay score. What we do is we grab that score's value vector and we weight it by how similar it was when we dot product, right? And then we go to the next word and say, okay, we dot the query and the key, and we dot it, and we get a similarity score, and we say, okay, I'm going to multiply that by that word's value vector. And then we go to the next word and we say, oh, I was really similar to you. So then we multiply that number, that really high number of this vector we care about a lot because it's close to us, by its value, right? And again, this idea of query key values is just so the model can learn to organize the space nicely and have that nice relation, right? What you get out at the very end is kind of like a weighted combination of all the other words which were important to you. And that's kind of the idea of self-attention, is that what it's doing to encode one word into the next is it first picks that word, it figures out how similar am I to all these other words, it gets a score, it normalizes it, and then it uses those scores as weightings to do a linear combination of those other vectors, right? So the idea is we're trying to, for a single word, we're trying to capture relevant vectors and meanings and words, and then combine them all together to produce a richer one. Right now, this vector here at the very end has some meaning of other words in the sentence and other meanings and things that were relevant to it. And now this can then be processed further, right? So that's kind of the self. Oh, this is a nicer one. So again, like let's say we look at the word booked. This is I should have shown this earlier. We do the dot product, right? The pass through the query key values, all that stuff. But again, the main idea is think we're dot producting all this vector with all other vectors, and we get how similar they are, right? This one's really similar. Booked in hotel. Ooh, again, very cherry picked, but the point. And then let's say room. Oh, that's another close one. And what we do is we use these as weightings and we multiply them by all their vectors and we sum them up. Oh, it says it right here. Look, 0.55 times booked, because booked probably has the highest score with itself. Then 0.15 with room, and then 0.3 of hotel. And we literally just combine all the vectors to produce the next hidden state. So again, our list of vectors we have, when we want to output the hidden state for it, we do this self-attention where we get the vector, we multiply with other ones, we get a similarity score, we use that similarity score as a weighting to do a linear combination of all the other vectors to produce a new, richer vector. Yes, Oliver.
This richer vector that is the output of one like repetition or hidden layer is equivalent to the token embedding plus positional embedding business that we had for our input. Like, is that correct? Like,
Yeah,
it's like, but for the
it's-
later.
it's a linear combination of those rich positional, semantic, and positional embeddings. But again, the side note is the thing in the very beginning, we process each of them in a different way depending on how they're used. If you're the guy multiplying with other guys, you pass through this one matrix. If you're the guy that gets multiplied by width, we call it a key. And if you're the vectors that are going to be used in the linear combination sum, you pass them through another network. Again, because if you didn't have any of these, you could do this as an algorithmic process. You could get vectors, multiply them, use that as a score, weight them, combine. There is no weights in this model. There's nothing learned. And what's actually helpful is if it can transform this vector into like, I am now asking. That's what the query, that's kind of the intuition, is the query network matrix transforms the vector into like, I'm asking. And then it transforms all the other vectors around it as in the relevance. Wait, let me see if I have the visual. Do I have the, hold on, let me, layer norm, did I get rid of it? I think it was down here. No. Yeah, okay. I'll speed through. So that's how self-attention works. One thing we have to do, because we're generating, is we do this masking. So what's happening is I kind of lied to you, as in we pick one word and we attend to all other words. And then we get the next one and we attend to all other words, produce the hidden. We actually can do this all at once. And that's the main thing. But the problem is if we do this all at once, that means like a middle word can attend to the previous words. Again, like the example with booked. So what we have to do is we have to mask out this matrix right here. We actually have to mask it out so that like the river can attend to the bank before, because the bank comes after the river, right? So what we do is we mask out this attention scores so that the model at training time, when it has a full sentence and you process all that parallel, it doesn't have the middle word attend to a word that doesn't exist yet. Because when we're actually getting it to generate, it tries to generate the next word, and to generate the next word, it's going to try to look for the next word, but there is no next word, it'll be 0, and it can't learn anything, and it'll do poorly. So we have to mask it out, so it can only rely on the words previous to itself to predict the next word, and not look at the next word, because it's like cheating. And that's the masked part of masked multi-head self-attention. So we almost got it, we get self-attention, we get the mask. The last part we need is multi-head. What does it mean by multi-head? Well, just like I showed the it and the connections, you actually have multiple different heads, multiple different pairs of query, key, and value matrices. In this whole process, it happens a bunch of different times. And what happens is so again, the first color I showed was orange, and I said the animal, but each head learns how to arrange the queries, arrange the keys, arrange the values in a way that they learn to combine in different ways. So one might be trying to combine verbs with their adverbs together. One might be trying to combine pronouns to the subjects they correspond to and things like that, right? So the idea is that we have a bunch of these query key value pairs that sit and do this entire self-attention process. And we have multiple of them, again, they're called heads. And we have each of them try to learn a different thing. Again, it's not as interpretable as verbs, combine adverbs, pronouns to the subjects, things like that. but we have it so each of these pairs of query key values can learn different ways of attending self-attention. Yes, and then.
And the last thing on that, then the multi-head part is not stacked multiple of these on top of each
Yeah.
other. It's stacked deep
In
in the
parallel.
same like layer almost, the same like same set of these.
Width-wise,
stacked.
yeah, exactly.
How are these heads like chosen? Like, is it automatically chosen by the algorithm or?
It's learned. So then, like, we can just have a single network learn what this So again, actually, I can just draw it here, right? This is the algorithm part. It does the multiplication, it scales it. It then does a multiplication here to do the linear combination, right? And that's all algorithmic. But it learns here the linear projection into the query, linear projection of the vectors in the key, linear projection into the values. And then again, we're not going to just do this once. We're going to have it so we're going to have a bunch of query key value pairs. Then the next query key value pairs, right? And those are where the learning happens. It learns how to transform the vectors.
Also, the very last thing you learn.
It was gonna. Yeah.
Sorry, so is this like multi-head business basically like kind of like ensemble learning or whatever? You just mash a bunch of like.
You're sure inside a network, you could think of if I solve three networks, I could just stack them and learn, but then in practice, it's kind of hard for them all to learn independent things, so it's better maybe train them, and that's why ensembling works, but then we can do training stuff to help. Yeah,
Yeah.
sure.
You're gonna look at proofs of why ensembling works with Venkat in 2 weeks.
Anywho, multi-head, we now know multi-head mass multi-head self-attention. Boom. That's the thing. Okay. Last part. Oh yeah, no, this is another visual. You have pairs of query. Let's say we just have two heads, right? Query key value. We have this other query key value matrix, right? And the idea is that each of these heads produce. Now let's say we just have two words in our sentence. Very simple. It produces another two richer vectors. I don't know why it's a different size, but whatever. And then each head is going to produce a different pair, right? So the first vector, like thinking, we got this richer thinking, and the next head produced a different richer embedding of thinking, right? And then if you have like say like n heads, like 7 heads, you're gonna have 7 different vectors. Which one do you choose to pass on to the next layer of the process, right? And this is where the linear part happens. Well, again, little idea. What happens if we just add all of them and we pass all of them to the next state? That's going to be insanely long of a vector. Like, look, our vector was originally size 3, and now it's like size whatever, right? So all we have to do after all this is what the linear part is for, is to aggregate and combine all the heads back, and we squeeze it all back down to a single vector, right? So we have each of the heads learn a different thing, and they learn how to process the adverb to verb, as pronoun to subject, right? These are all different ways the heads have learned how to process it. And then what we do is we just do a single linear at the very end of this block, which projects it, all these output tokens from all the different heads and learn the relationships. And we just do a single matrix and we project it down so it becomes the original size it was in the beginning, right? Because again, if we try processing every single head's learned how to process like rich embedding, it'd be too complicated and expensive because then it's now this giant vector has to be processed 7 different times. We have to have 7 of them, and it's too massive, right? So what we do is we compress it back down so it can pass on. Make sense? Yeah. So that's the feed forward part. It's just so that we can chain together these layers of blocks, right? So it's pretty much now what we've done with a single block is we have our vectors. It does all the self-attention, all those things I explained, right? Multi-head, whatever, but project it down. And at the very end, the vectors are just the same size. It's just another new list of vectors. But now they have richer meaning in them, right? And the hope is that if we keep processing them enough, they can have really rich meaning, right? So again, this is the thing. Yeah, this allows for a new embedding to stay rich while representing all the heads and staying the same size as the original. So now we repeat n times. And what's really cool is that as you repeat this n times, you actually gain the attention heads don't just capture word relations, they capture higher level like language relationships, right? Because these vectors aren't representing words anymore. They might be representing entire sentences or ideas. And then the attention heads aren't attending just words, this word, adverb. It might be even capturing like sentence relationships and different meanings, right? So at higher levels of attention heads, the what they're capturing, the relationships they're capturing are actually higher level language because each of the tokens aren't just words anymore. They're more richer things that represent a sentence or ideas, right? So like each layer, the tokens now are richer and richer and richer. And that means attention heads have to be capturing richer relationships, which is kind of cool. Just to think about kind of that like mixing property. So yeah, at the very end, we process it a bunch. We have these now list of really rich things. And how do we make it so, what's the training objective? What do? What we do is we grab that thing, remember, just like before, we grab the vector, right? And we say, we pass through the linear softmax, we project it into all the words, and we say, what we want this, like, let's say it's like 3 words. We want let's say we grab the third word and we do all this processing. We get the embedding out. What we want it to classify as is the next word in the sequence. And let's say, what about like the next 4 words? What do we want that process one to be? We want it to be the next one in the sequence, right? Same thing as like BERT and all these things and RNNs. The idea is that by having it so, the word vector has to get captured enough rich meaning of a sentence to produce a rich enough vector that can be used to classify the next word. It must be really good at understanding language. That was a little verbose, but yeah. Any questions? Yeah, so this is the training objective. Again, let's say we have, oh, I should have used this slide. LLMs, whatever that is, are cool, right? We have the cool, or no, we're not doing cool. We're doing cool? Yeah, we have the word cool. And when we pass it and we say cool, the cool vector passed through a linear should predict the next word here, whatever that word is, right? But again, we can do this all at once because we can pass all these through, again, with the masking, the matrix, we can do all that dot products, self-attention, all that stuff, process all of them, and we have each of them pass through a linear. And we say this one should be this guy, should be this guy should be this guy, this person should be this person, and so on, right? And we can from one sentence, we actually can get like however many words as training examples. So it's a 10-word sentence. You now have 10 training examples. No word, what's the first word? 1 word, what's the second? Right? And so on and so forth, right? And again, through this training objective of predicting the next word, it actually can do all this magical stuff. Again, if you want it to like follow instructions, you can just train it on given it, if I say to do something and then like I put a $sign, I then expect the next words to be following that instruction, right? And this kind of idea of instruction tuning. How much time? Okay, yeah, well, it's good actually. So yeah, real fast, GP3 case study. I think we already looked at this, but yeah, GP3, massive, a lot of money, really big. But let's look at the results, right? Because this is kind of important to actually see it in practice and what it looks like as a base. Because ChatGPT is not a base model. It's actually, they did some stuff to it. So again, at first, this was crazy. This is my high school AP Gov assignment. I did it very well.
I remember doing that.
Really?
I went through, we put in AP exam prompts one day.
It was
the
so
dev
good, it was
console,
so
and
good.
Just had fun, just like, I think I sent some of my high school history teacher to get her to grade them. You know,
Did you like them? Oh,
I mean, we cherry picked.
The funny thing is, was really good, is that in the homework, they gave me 2 examples of how to do it. And what ChatGPT is really good at is following examples. So I do look at this though. Every election from 19, like that's insane. Okay. Anyways, it was great. But where did it fail? Let's say I asked, like, this is what happened if you used it back then. You said, explain the moon landing to a 6-year-old. And it would say, explain the theory of gravity, explain the why is it doing that? Well, that's probably what it's seen. Probably maybe a test bank or something. And if you ask a question, maybe it's just a bunch of list of questions, right? It's not actually good at following instructions. Yeah. Another good example is like, let's say you ask it, what is the purpose of this code? And you give it a code. It will output an A, B, C, or D. That is not you. What? How? Like, what's? I wanted an answer, not like. But think about it. If it had a question, then a code example on the internet, what is most likely to follow? Like
Chag.
Yeah, like the Chag, like the like a test bank or something. So it makes sense. But how do we get it to beat ChatGPT where we're like asking it to do something and it actually does it, right? Yeah, data from internet. Again, what you could do is give it shots and examples, like my AP Gov assignment, right? So this was called shots. This is called 0 shots. You just say translate from English to French, and then you just say, Chief, what should it be, right? But what happens with GPT-3 is if you actually just give it one single example, you just say translate into French, you show the how you want it to do it, and then you ask. Its performance goes from like literally 10% to now up to 50%, right? And it's really hard to see with these smaller models the scaling well. But what happens is with this really big model, this is 1.3 billion, this is a 13 billion GPT-3, and this is 175 billion. Just one example, 10 zeros 1, just one shot example of showing it something, it got 50% accuracy on tasks, which is crazy. And then if you give a couple of shots, this is a few shots, if you give it a couple, it does even better, right? So it's not that it's dumb by just saying it, blah, 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 explain. It's actually really smart. It's just it doesn't really know what you want from it. And that's the main thing. Again, the paper, just one example. Yeah, the paper name is this is the GPT-3 paper. Language models are few-shot learners. It's not language models are zero-shot learners. Like that's the name of the paper. It's that they're really good if you just give them a couple examples, which is this crazy power of, again, generalization, just given a couple examples because it seems so much. Once you tell it a little bit of what you want and show it, it's really good at that. So yeah, the question though is how do we get it to be a good zero-shot learner, right? Which is what ChatGPT is. You don't give a bunch of examples, right? So basic idea, actually I'll just show you. It's InstructGPT. This is the paper that pretty much is what ChatGPT does today. And this is the result. Instead of explain, it actually went and did it, what you're used to, right? Again, this example from before, boom, look at that. It actually explained the code. Thank you. So how do they do this? Do they give a bunch of examples? Not really. They did the thing I said where you kind of just give it, I didn't say it actually. But you pretty much just have like explain the moon landing. You just have a human write the right response, and then you just have it fine tune and train longer on like human, like what a good response looks like. Like that's a pretty basic thing. And that does, oh yeah, also that thing, they paid like Kenyan labelers like less than $2 an hour. Yeah, anyways, but it works better. Look, this is GPT-3, this is GPT, and this is like the biggest model, right? This is GPT when you prompt it, and this is it fine-tuned. So what this shows you though, this is a human preference scale. Even the 175 billion parameter model, if you just give it a couple examples, if people like it more than even the 1.5 billion, better than the 175 billion. And if you fine-tune a 1.5 billion model, very, very small compared to 175 billion, people still prefer way more than 175 billion. I mean, it makes sense because if you look at this, I don't care how smart it is. If that's the output, I'm not going to care, right? So yeah, so arrows, yeah, it outperforms it, right? But InstructGPT is the last thing. What it does is it tries to go a little bit better, right? It's a little process called reinforcement learning from human feedback. It's called RLHF. Basic idea is that you have this, again, this example of explain the moon landing. The model produces a bunch of responses. A human ranks those responses, and we train a separate model that is completely separate, like a really small, maybe GPT-2 something, right? And we have that learn how to rank the responses and learn human preference. Then what we do is we then ignore that process. We have this model that knows human preference. We have the model, we prompt it, generate story. It then generates it. And then we have that reward model to say, how well did it do? What would a human say this is good? And we have that as a signal to inform it. And then we do this kind of reinforcement learning, feedback, positive reinforcement. And again, it's not a human sitting there saying, no, I like it. Yes, it's good. I'm gonna give it this rating. We train the model to learn a human rating, and then we use that to then do a training process, right? And it works. It works. This is InstructGPT. It works way better. And this is pretty much how a lot of this kind of tuning zero shot is done today. Yeah, so again, idea. You pre-train the model on normal response data using transformer architecture, predict next word. You can supervise fine-tune it, have humans write like the good response. And then you do RHF where you train a little reward model and then you do feedback. And this is like the general idea. That's how you make ChatGPT. There you go. I'll speed that. Okay, yeah. These are LLMs right now. That's Meta. OpenAI has GPT-4. Gemini is released. Gemini Advanced Ultra released. You can buy it with their 20 terabyte whatever thing. It's cool.
Stability also came out with stable thing. They're working on a /day release at some point.
Yeah. These are all the things. Oh, that's funny. These are all the things. What are transformers use today? A lot of places. That's the slide.
Let's talk about vision transformers.
Yeah.
Next time.
Next time? Okay,
Yeah.
next time. Last thing, what do I want to show? Oh, this is the last thing, I guess. I just want to explain this. Attendance scores, like I was saying earlier, are really good. This is what I was pointing to. Attendance scores are really cool, but they can be deceived. This is a cool paper about it. Even though, like, again, that tending, and you can, like, people thought you could use it to, like, look at, oh, it's using this and it's being sexist or something. There's a really easy way to get around it. You just don't let it attend to those words, and it still learns how to be, like, some kind of bad thing, like racist or sexist, even if its attention scores don't show it. It's very easy, but because these models on default are really good at, like, they normally tend to look at the word and have a high magnitude towards the word they're looking at, people are like, this is interpretable. But what these researchers did, this cool paper, they literally just said, don't show the magnitude, and it was still able to act very sexist, even though it didn't show it. So just looking at the model weights, we thought interpretable. It really isn't. It can hide it. It can do a lot of deceiving. So model interpretability is still, not very great these days. Yeah.
But yeah, I think we're out of time for LLMs. Again, like there's so many other things we can talk about for that.
Only 5.
Yeah, we have a lot of things. Basically, next week, it's actually in 2 weeks because again, President's Day. We're gonna talk ensembles and apps on DD privacy. It's gonna be another one of our special Venka does a proof in front of you sessions where you actually get to learn why ensembles work really well mathematically. And if you're wondering when we say next time in terms of we have more things about LLMs coming soon, if you look at the roadmap here. The very last week, week 9, we're going to talk about deep learning models and modern deep learning, which is going to be this like mishmash workshop. We just talk about everything we couldn't talk about in all the previous workshops, including more things on LLMs, efficient neural networks, reinforcement learning, and of course, my favorite topic, diffusion. So if you have any topic that you want us to talk about that you think is fun for week 9, let us know, because this has been different every quarter that we have been doing this. But yeah, thanks for coming. Hope to see you in 2 weeks. Woo!